In this electrical circuit, we want to see how the response of VO is affected by our input VS, when our source voltage is going to be a step input with an amplitude of 5 volts DC. So first thing we're going to need is our diagram, because we are going to need to develop the transfer function that relates VO to VS. So I'm going to make a simplified version of this that is going to take into account the impedances. So I'll call this Z1, and then it's going to go through a second impedance block, Z2, and I'm looking for the voltage across that second impedance block. So this is going to be my VO. So I can use this diagram to create my transfer function. I want V out over Vs. Well, I can do that using a voltage divider in order to save time. So V out over Vs is going to be the impedance Z2 over the total impedance Z1 plus Z2. Now I do need to define my Z1 and Z2. Z1 is simply just R1, and then Z2 is going to be the capacitor and resistor 2 in series, so I can add their impedances together. So 1 over Cs plus R. So we can rewrite this as 1 over Cs plus R over R1 plus 1 over Cs plus R. And this is R2, and this is R2 here. Now, it's not in any standard form yet. I don't want s's in the denominator of the numerator or the denominator itself. So what I can do is multiply top and bottom by Cs and rewrite this initially. So in the numerator, 1 over Cs times Cs is going to be 1 plus RCS. And in the denominator, I'll have an R1 C times S plus a 1 plus an R2 C times S. And still not in the form I want it. The numerator, I want descending powers of S, so RCS plus 1. And then in the denominator, I am going to have here an R1 plus R2. I can pull a C out times an S plus 1. So this is now in at least the form where I have descending powers of S. And if I look at what this system is, based on the denominator, it is a first order system. I have an S term and I have a 1, but now my numerator, I have an S term and I have a constant. So it is a first order system, but it's in a form where I have an S in the numerator. So in order to sketch this response, the V out over Vs, I am going to need to separate this into a fractional part and a constant part. So I could do this algebraically. I'm going to actually at this point apply my values, and I'm going to do it numerically instead. The algebra, it's just going to be a little bit messier than I want to get into right now. So if I apply these values, and I have to specify which R this was on the top R2, these are all R2s coming down. Okay, so that's now specified. I was given to use that R1 is 7, R2 is 5, and C is 0.3. So let me apply those down here specifically. So R2 of 5 times a C of 0.3. That means on the top, I'm going to have 1.5 times S plus 1. And then in the denominator, I have a C of 0.3 times R1 plus R2 is 12. So I have a 12 times a 0.3. So in my denominator, I'm going to have 3.6 times S plus 1. Now I can rearrange this into a form that is going to be useful for me to do some sketching. So I need to separate this fraction out into a constant term and then a fractional term. So I can use here polynomial division to do that. So I'm dividing 1.5s plus 1 by 3.6s plus 1. So with the polynomial division, what I want to do is I want to look at the leading coefficients and do that division first. So I want to see how many times does 3.6 go into 1.5. Well, certainly less than one time. It goes roughly 0.417 times into 1.5. So again, that's to say that 0.417 times 3.6 is 1.5. Right? I don't need an s on top because 0.417 times 3.6s is the 1.5s. And what I want to do is subtract then this 0.417 times my divisor. So 0.417 times 3.6 is 1.5s, and that's what we wanted. And then 0.417 times 1 is going to be 0.417. All right, so I do this. So by design, the s terms are going to go to 0, and now I'm left with 1 minus 0.417, which is going to be 0.583. So the next step in this polynomial division would be that I would now take this 3.6s and see how many times it goes into 0.583. But at this point I need to stop because my 3.6 has an s term. I don't have any more s terms left. I'm just at 0.583, so that would tell me to stop. So I can use this information to rewrite my fraction now. Because what this means is that my whole number part is this 0.417 plus whatever I have left over, the remainder, 0.583 over that divisor, 3.6s plus 1. So this is another way to express my transfer function VO over VS. And now this is in a form, it's not that standard form where I wanted one fraction with descending powers of s in the numerator and denominator. We already expressed it that way. This is now in a form that's going to be convenient for sketching. When we go to actually plot it in MATLAB, then we'll go back to that form with descending powers of s over one fraction. All right, so how does this help us for our sketch? Well, let's see how we can use the constant term and the fractional part to make our initial sketch. So we can identify some different features here. We have our tau value is 3.6 seconds. And again, I just want to make sure we're always checking that this term is 1. So nothing to rearrange further in this one. The constant term in that denominator is 1. So that means that our tau value is 3.6 seconds in this case. Our a is 0.583. That's the numerator of the fractional part. Capital C, the whole number part in front, or the constant out in front, is 0.417. And then B, the amplitude of our input, is 5 volts DC. We're working in base units, so that's going to be 5 volts. All right, so now these 4 parameters are enough to get a sketch of our system. So we'll have time in seconds, 0, 1. Right, so my sketch, I'll just go out for 8 seconds here. And then I'm going to go up to 5, 4, 3, 2, and 1. Right, so this system, because we had that s in the numerator, we are going to immediately have a jump up to our first value. So our first value here is going to be b times c. So bc is going to be 5 times 0.417. So at time 0, or really just to the right of 0, we're going to be at 2.083. So just above 2. And let's look at our steady state value. The steady state value is going to be b times c plus a. Well, c plus a, 0.417 plus 0.583 is 1. So our steady state value here is 5 volts DC. So I'll put my line up there. That's what we're asymptotically going to approach. We're starting at about 2, we're going up to 5, so we're going to approach asymptotically from below, going up and up and up, getting closer and closer to 5. So the last thing I want to put on my sketch here is my value at the time constant, so 3.6, so 3.6 seconds. Well, what we're going to have there is we are 63% of the way between our starting point and our steady state value. So that means that our v of tau is 0.63 times the difference between the steady state and our initial, 2.083, plus our initial value. So v of tau is going to come out to about 3.92 volts DC. So almost 4. So right about here is going to be the value of our voltage, our output voltage at our time constant. So we have this initial jump up. We are then going to pass through that time constant, and we are going to asymptotically approach from below a value of 5, our steady state value. So this is our rough sketch of our system here, and we see here where we had that s in the numerator causes that initial jump at time 0 or just to the right of 0, and then we proceed with that asymptotic approach to our steady state value. So let's see how well our sketch does versus actually putting it into MATLAB. Now, just as a reminder, in MATLAB, I am going to put in the transfer function in the standard form where I have descending powers of s. So we're going to see the 1.5s plus 1 as our numerator and the 3.6s plus 1 for the denominator. MATLAB wants it in that original form in order to do the step input. Going into the MATLAB portion now, I will create this transfer function. So just double check it. So this is in the original form. We don't need to split it into a constant and a fractional part. This is what we want to put into MATLAB. And we have a step input of 5 volts DC. So I will enter that. And then we're going to apply that step function. So step of b times g, so our amplitude times the transfer function itself. And I am going to simulate this over 25 seconds. So let's see what this whole thing looks like. All right, so this is our response. Let's see how close we got here. We said that at time 0, it was going to be about 2.083, and we're really close to that number. So basically, we're right on top of it. So our initial, or just to the right of 0, agrees with what MATLAB has in the numerical simulation. Now let's look at our second plot point. We want to know the value at the time constant. So let's first find that on our plot here. Keep that and add 3.6 seconds. All right, so 3.6 seconds, we have a value of 3.927. And that matches the value we had of 3.92 in our hand sketch from using the parameters in the transfer function. So that matches. And finally, our steady state value, going out to 25 seconds, we see it's asymptotically approaching, it's flattening out, and it's getting closer and closer to 5. If we went out a little bit further, we would get even closer there. So our steady state value of 5 volts DC, that also agrees with what we found by hand. So the actual plot out of MATLAB at these key points is matching exactly what we had in our sketch. The sketch does not capture the exact behavior of the system, but at these key features, we are exactly matching what we have in this numerical simulation.